Okay, good day to everyone. We are from Group 3, and today we are going to present about the in vivo nanosensor, which particularly in the in vivo fluorescent nanosensor for the hydrogen peroxide detection. Okay, so for information, in vivo biosensor enable the real-time monitoring of the biomolecule within the living organism. So a typical biosensor will consist three main parts, which is the analyte, so the target molecule can be detected, and also the biological recognition element, which is the molecule or chemical group that specifically binds to the analyte. And thirdly, which is the transducing element, which will convert the interaction from the biological recognition element and also analyte into a measurable signal. So these components work together to enable the selective, also sensitive, and also fast detection of the biological signal. Okay, so how a biosensor transduces signal? We can see from the figure, only the right analyte can be bind to the recognition element, which they will use the transducer to transduce the signal for a specific function. So in this particular example, hydrogen peroxide is the analyte. So hydrogen peroxide acts as a reactive oxygen species, which will be produced during the oxidative metabolism. So it will involve in the immune response, host defense, and also cellular signaling. The excess amount of the hydrogen peroxide can damage protein, DNA, and also RNA, and this will contribute to the disease such as cancer, diabetes, cardiovascular disease, and also the neurodegenerative disorder such as Parkinson and all that. So by monitoring the hydrogen peroxide level is quite important for detecting the oxidative stress and also related disease. While for the biological recognition element is the phenylboronate group. So we can see the reaction over here. The phenylboronate is react with the hydrogen peroxide and they will transform into phenol and also the borate species. So the probe is called the phenanthroimidazole benzonitrile phenylboronate. So they will use the phenylboronate group as the recognition element. So hydrogen peroxide will selectively oxidize the phenylboronate into the phenol. So this is a selective and also fast chemical transformation that allowed the detection of hydrogen peroxide over the other reactive oxygen species. So this also activates the fluorescent via the intramolecular charge transfer by converting the non-fluorescent probe, which is in the off state, into a fluorescent state. So it's in the on state. And lastly, the transducing element is the intramolecular charge transfer fluorophore. So the transduction occurs through a fluorescent ICT mechanism, which involves the phenanthroimidazole, which is the electron donor, and also the electron acceptor, which is the benzonitrile. So when the hydrogen peroxide react with the phenylboronate, the electron flow is altered. So the ICT also disrupted, so the fluorescent intensity will be increases from weak to a strong emission around 480 nanometer. So the fluorescent will appear within 8 to 10 minutes after the exposure to the hydrogen peroxide.
Assalamualaikum everyone. My name is Ahmad Danish. Now I will continue the presentation on the mechanism of detection. Our biosensors consists of three main parts. The first one is the PAM, which is the light emitting component. Next, we have the BN, which is the electron withdrawing group. And the last one would be the PB, the recognition site for our analyte, the hydrogen peroxide. Next, before the detection, meaning when there is no hydrogen peroxide, the PB group keeps the probe in an off state, meaning we will see no fluorescence. As you guys can see, the first picture up there, and the ICT between the PAM and also BN, it stops the fluorescence. When there is hydrogen peroxide will oxidize the PB groups, converting it into a phenol. This is where we can see the fluorescence, the blue color in the picture. The fluorescence color can be related with the presence and also the concentration of hydrogen peroxide. Now we will continue on the biological target. So for our biosensor, the target will be the hydrogen peroxide, a reactive oxygen species. Why do we want to detect the hydrogen peroxide? This is because the hydrogen peroxide can actually be associated with several diseases such as cancer, diabetes, cardiovascular disease, and also neurodegenerative disorders, including Parkinson's and also Alzheimer's. By detecting the level of H2O2, we can actually use the biosensor as a useful tool for early disease detection, monitoring progressions, and also to evaluate the active antioxidant therapy.
So moving on to the spectral properties and sensitivity. So spectroscopically, this probe has an excitation at 410 nanometer and emits around 480 nanometer. It detects hydrogen peroxide linearly up to 150 micromolar with an impressive detection limit of 148 nanomolar. So next will be the selectivity to the hydrogen peroxide. So the selectivity test show that the probe responds strongly to only to the hydrogen peroxide and not other reactive species like OH radical, hypochlorite, or antioxidant like glutathione. You can see that the ONO minus shows minimal interference. So continue with the chemical reactions. The equation is as shown in the slide. So the PAM-BM-PB it reacts specifically with hydrogen peroxides, converting its phenylboronic group into a phenol and forming PAM-BM. So this fast reaction, which typically under 8 minutes, it blocks the ICT process and turns on fluorescence, enabling a real-time H2O2 detection. So continue with the molecular characterizations. So it includes the UV-Vis and also fluorescence spectroscopy as well as the HOMO, LUMO, orbital analysis to confirm our ICT. And then the mass spectrometry also can help to confirm the chemical changes during sensing. And then this slide shows the reference that we refer when completing this assignment. That's all from us. Thank you for listening.